Greetings and welcome to this special lecture on an Odyssey in atomic physics. This is a special lecture for which I want to thank NPTEL and the National Knowledge Network. And the subject is vast, and in a certain sense it is like taking a journey in the Himalayas. So that is the first picture you see on the screen. I wish that some cool breeze from the Himalayas could flow into Chennai this afternoon. It is terribly hot and humid over here. But the nice thing about a voyage in the Himalayas is that no matter which part of the voyage you take, means you can cover only so much ground. There is no way you can cover the entire ground, and I have no aspiration that I will be able to cover the field of atomic physics in any significant manner. So we are going to get just a small glimpse of the entire field. But no matter how small a trek you take in the Himalayas, it can be a very beautiful experience because it is the world's largest stunning mountain range, and I hope that the journey will be an enjoyable one even if we do not quite get to the summit. So the development in atomic physics interlaces development in quantum mechanics, and this lecture is addressed to senior college students in particular, and therefore not a whole lot of background in quantum mechanics is assumed, because some of quantum mechanics will be developed, at least the salient features will be mentioned in this lecture because they are important for any comprehension of the subject. So you would have heard about certain developments in quantum theory, and I will touch upon some of those things, but then I will also make an attempt to give you a flavor of some of the nice things which are happening at the very forefront of research in this field, which have important and very exciting consequences also on engineering and technology. So the importance of this subject can hardly be undermined. Means if you just look at the last 3 decades from 1980, there have been roughly speaking about 2 Nobel Prizes in the general field of atomic, molecular and optical physics, to which atomic physics constitutes a subset, and roughly in every decade 2 Nobel Prizes are awarded to this, at least in the last 30 years. So it is a very important field, even as scientists are working at getting very cold temperatures and cold atoms, the field itself is very hot and lots of things are happening in this field. Now the idea of an atom is a very ancient one. It is a very old one, and perhaps the first credit for this idea should go to Maharshi Kanad, who lived presumably around 600 years before Christ, and what he did was to make an attempt to comprehend the universe in 9 elements, and these 9 elements were earth, water, light or fire, wind, ether, time, space, mind or soul, and then every physical object Kanad proposed could be considered as made up of small elements, tiny elements, which he called as an anu. So this is the first, historically perhaps the first idea of an atom. But in the sense of modern science, this idea took a detailed structure in the ideas of John Dalton, and this was just a little over 200 years ago. Who was born in a small modest family in England at Cumberland, and Dalton's book came in 1808, The New System of Chemical Philosophy, and what he proposed is a set of 5 fundamental postulates. that all matter consists of tiny indivisible particles called atoms, that all atoms of a particular element are exactly alike, but atoms of different elements are different. Now this is very nearly true even as atoms are understood today, with a small difference, because one knows that an atom has got a structure, and in the nucleus the number of neutrons could be different, so there are different isotopes. So all the atoms of a particular element are exactly alike is perhaps only approximately correct, but not very wrong. So I think it is amazing that Dalton could make such bold hypothesis, which turns out to be very nearly correct, that all atoms are unchangeable. This is also very nearly correct in the gross sense, but not quite in details, because of course you can break the atom has got a structure, you can ionize, you can pull out the electrons, you can have ions, you can even get into the nucleus, you can even have fission and so on, and there are elementary particles to talk about. That atoms of elements combine to form compound atoms, and this is a nice idea, because in this sense, if it is not taken very much out of context, one can understand atoms to be some sort of ingredients of which condensed matter is made. So composite matter, condensed matter, is made up of these atoms, and therefore it becomes very important to understand atomic properties so that you can interpret the properties of molecules, clusters, bulk material, solids, and so on. And his fifth assumption was that in chemical reactions atoms are neither created nor destroyed, and the conservation of matter holds pretty much as we understand things today. Of course there are these relativistic consequences, and these add some finer niceties to these postulates, but by and large the 5 postulates made by Dalton are quite robust, and they constitute the beginning of modern atomic physics. Now let me show you a spectrum, and this was taken in the 19th century by Angstrom, and Angstrom developed some of the first high precision spectrometers, and these are measurements in 1853, and this is the spectrum of the hydrogen atom, and this is something which you find in most of the universe very easily, because hydrogen is present everywhere. So it is an important atom to study, apart from the fact that in the periodic table it is the first atom, it is also the simplest atom, it has got only 2 particles, one proton and an electron, and that is it. So it is the easiest atomic system to work with. And in the visible part of the spectrum there are these 4 lines whose wavelengths are mentioned over here, 6562.1 angstrom, and then there is one at 4860, one at 4340.1, and another one which is perhaps not very clearly seen in this picture, but it is very much there, I promise, which is at 4101.2 angstrom units. Now it is tempting to ask if there is any pattern in these numbers. Now why should one even ask such a question? Because if we think about some numbers like 2, 4, 6, 8, 10, 12, 14, immediately you recognize the pattern, or 3, 6, 9, 12, or 5, 25, 125, and so on, right? You could immediately recognize the pattern. When you look at numbers like 4101.2, 4340.1, 4860.74, why would one even look for a pattern in such numbers, let alone find it? And this was the situation in the 19th century, that these numbers were there, and Balmer, he actually found a pattern in these numbers. He found that these numbers fit this formula which is in front of you, that the wavelength is given by n square upon n square minus 4 with a certain proportionality constant b, which is not there is nothing obvious about the proportionality number b, that Balmer found. This number turns out to be 3645.6, which is quite an odd number to think about, but Balmer actually found this out, that all of the wavelengths which were reported by angstrom actually fit this particular formula, this relationship, all of them. And if you just put different values of n, put n equal to 3, 4, 5 and 6, then you can regenerate these 4 numbers. Now this was an amazing discovery. Now perhaps the fact that Balmer was teaching mathematics in a girls' school at Basel, that might have sharpened his mathematical and especially numerical skills, and that may have been responsible, and he discovered this relationship when he was in his 60th year, so there is hope for older people as well. And Balmer got this formula, it worked for the hydrogen atom spectrum, and not only that, Balmer went further. He predicted that there would be other lines which were not seen, which were not recorded in the angstrom spectrum, because they did not belong to the visible part of the spectrum, but they were there in the electromagnetic spectrum. And Balmer predicted that there would be other lines, perhaps in the infrared, corresponding to n equal to 7, 8, etc. Not only that, he also predicted that the number 4, which is over here, could in fact be replaced. This number 4 happens to be the square of 2, but this could be replaced by the square of 3, by the square of 4, by the square of 5, etc., and you could get additional lines, and this was Balmer's prediction, and one knows now that these lines in fact have been observed, and they constitute the entire spectrum of the hydrogen atom. Now a few years later, this was about 6 years later after Balmer's work was in 1884, and in 1890 Johannes Rydberg, he found that the hydrogen atom visible wavelengths could actually be fit to another formula, which is nothing but Balmer's formula, but for the inverse wavelengths rather than for the wavelength themselves. And Rydberg also found that this formula could explain all the wavelengths that were seen in the hydrogen atom spectrum. And it turns out that Rydberg was not quite aware of Balmer's work, but he arrived at this relationship quite independently, even if it was 6 years after Rydberg. So great minds do think alike, even if they are not in touch with each other. Now this is a semi-empirical relationship, and you know what a semi-empirical relationship is. A semi-empirical relationship is one in which you make use of experimental data. So there are some observed quantities, and you come up with some model which will explain the observed spectrum. So the bias, the prejudice provided by the experimental observations is an integral part of an empirical formula. So this is an empirical formula, it is not based on any fundamental theoretical model, it is not coming from quantum mechanics, for example, and this is this belongs to the 19th century when quantum mechanics was yet to be developed. So this was essentially a semi-empirical formula, but it turns out that it holds good even in modern quantum theory. Now the next event that I should mention in the development of atomic physics was this model by Bohr and perhaps its modification, which admits elliptic orbits. So these are the circular and the elliptic orbits of what we call as a Bohr-Sommerfeld model. This is sometimes also called as a planetary model of the atom, because what this model envisages is that electrons go around the nucleus in circular or elliptic orbits much the same way as planets go around the sun in a solar system. Now this was proposed by Niels Bohr in 1913, and in a certain sense this is also a semi-empirical model, because it is based on a certain set of postulates which Bohr made. It is, to a certain extent, it is a quantum model, but this is what one would call as old quantum theory rather than the quantum theory as we understand it today, and I will make a distinction between old quantum theory and what has now come to be known as quantum theory itself. The reason is the following, that if you ask for what is the central problem in mechanics, it is essentially this, that how do you characterize the state of a mechanical system and how does this state evolve with time. That is the fundamental question in mechanics. Now in classical mechanics this question is addressed, and the first persons to come up with a rigorous answer to this were Galileo and Newton, and this is contained in Newton's laws of mechanics. So Galileo's law of inertia which was integrated into Newtonian mechanics as the first law of Newton. In this, the fundamental assumption is that there is a linear response mechanism, and this governs the temporal evolution of a mechanical system. So this is explained, this explains how a mechanical system evolves with time, and what it does is that it characterizes the mechanical system by these two parameters, the position q and the velocity q dot, which is dq by dt, which are represented as q dot. So the position and velocity must be known to represent the mechanical state of a system, and then certain equations of motion which govern the time evolution must be solved so that you find out how the system evolves with time. Now an equivalent formulation of this mechanics is in terms of Hamilton's principle of least action, which also begins with the fundamental consideration that the system is characterized by position and velocity or position and momentum, and then it sets up the equations of motion, either the Lagrange equation of motion or the Hamilton's equations of motion. Now all this is fine, but we immediately note that unless the position and momentum is known, and these are the initial conditions which must be fed into the equation of motion, okay, when you integrate the equation of motion to get the solution, the initial position and the initial momentum must be fed into the solution so that you can get the complete answer. Now if you cannot get this information, where do you go? Then this scheme will not work, and if you cannot get this information, then you cannot get these circular trajectories, you cannot get these elliptical trajectories, and the essential requirement of position and momentum is something that is assumed but not guaranteed by nature. Okay, it is assumed by us when we set up an equation of motion in classical mechanics, but it is not guaranteed by nature. And in terms of these position and momenta, we characterize any physical observable as some function of q and p, but it all rests on the assumption that q and p are simultaneously knowable at all. Now comes the interesting question, how do you get this information about position and momentum? So fair enough, all you do is carry out a measurement, find out what the position is, get an answer, record it, then conduct another experiment, find what the momentum is, record it, and you have your answers, there you go. Now it is not as simple as that, because what happens is that if you perform a measurement of position, you record it, you get an answer, no problem with that, then you perform a measurement of the momentum, you get an answer, no problem with that either. But if you come back and repeat your measurement of the position, and if you now get a different answer, where do you go? Which answer would you take, the one that you took at the first time or the one that you would take the second time, or would you take an average? So it turns out that every time you perform a measurement of the position, you disturb the momentum of the system in some uncontrolled manner, and nature hides this from us, so we cannot get that information, and the result is that position and momentum cannot be known simultaneously and accurately, which also means that there can be no orbits. So, the Bohr-Sommerfeld picture, the planetary model of the atom, which seemed to work and provided some information, which is what we called, which is why I call it as old quantum theory, because we know now that it cannot work. These orbits cannot exist because the orbits require for their existence simultaneous knowledge of position and momentum. So, there can be no orbits, and this is a very nice title which I recall from the book by Banish Hoffman called The Strange Story of Quantum, in which she has got a chapter called The Atom of Niels Bohr, and in the next chapter in which she analyzes the Bohr's model and shows that it really breaks down, it has got a very nice title, that the atom of Bohr actually Niels. Okay. So, there can really be no orbits, and we cannot therefore follow the classical scheme either of Newton or of Lagrange or of Hamilton to answer the fundamental question of mechanics, that how do you characterize the state of a mechanical system and how does it evolve with time. So, this question must be answered using on a completely different platform, and this platform is provided by quantum theory. What quantum theory does is it provides this alternative, that you characterize the state of a system by a vector. This is a vector in the Hilbert space, and dynamical variables must be characterized as operators, and these operators would operate on the operands, which are the vectors, and then by carrying out the algebra further, as Dirac tells us in his book Principles of Quantum Mechanics, by carrying out this analysis further, one extracts physical information about the system. So, there is a whole algebra, there is a whole mathematical formalism of quantum theory that one must employ to get information about the system. But the system is now characterized by a vector, which I denote by this particular symbol over here. This is called a ket in our language. So, this is the ket vector in the Hilbert space. So, the Hilbert space was named by John von Neumann in honor of his guru David Hilbert. So, now we have got these kets, and we are going to need these ket vectors for an atomic system, and we will begin our discussion with the simplest atomic system, namely the hydrogen atom, and we are going to ask, how do you label this ket vector? It has to be designated. So, we need a label for it, and our quantization has been achieved by making this beginning, that the state of the system is characterized by a vector in the Hilbert space, and dynamical variables are represented by operators, the position q by the position operator, the momentum p by the momentum operator. So, the dynamical variable f itself becomes an operator in quantum mechanics. Now, to get the labels, what we do is operate on the operand by the operator and find what kind of new vector you get, and if this new vector happens to be proportional to the old vector, the one that you started out with, then you have an eigenvalue equation, and if you construct this eigenvalue equation, then you can use this eigenvalue itself to label this vector, because that is some information you can get about the state of the mechanical system. So, the mechanical system can be characterized by whatever you can measure about the system, and you perform this measurement of some dynamical variable which is represented in quantum theory by an operator, and you operate by this operator on the state vector, and the eigenvalue will be used to label this vector, and then you have the complete eigenvalue equation which you would have met earlier. So, now we have some mechanism to start labeling the state vectors, and we are going to find the state vectors for the hydrogen atom. Now, this is quantum theory, and this was developed by Erwin Schrödinger, and this is the Schrödinger form is known as wave mechanics. The matrix mechanics was developed by Werner Heisenberg. The two together constitute quantum mechanics or quantum theory, and it has inbuilt statistical and probabilistic considerations, and this is encapsulated in the famous uncertainty principle, that the product of the uncertainties in position and momentum must exceed h cross over 2. The lowest value it can attain is h cross by 2. So that is, there is a minimum uncertainty, there is a probabilistic consideration, it is also there in the Max Born's interpretation of the wave function and so on. So there are these statistical and probabilistic considerations that you cannot escape from whenever you have a quantum picture. Now Einstein was very uneasy with this, and he did not like the probabilistic elements in quantum theory. So it was his conviction that God's scheme for natural phenomena could not be based on statistical or uncertainties. Okay, this was his contention, this was his conviction, and in fact a famous quote attributed to Einstein is that God does not play dice, because it's like a game of dice which has got probabilistic consequences. So this is something which Einstein would rather eliminate from his mindset. Now Einstein came up with plenty of arguments to find holes in quantum theory, to disprove quantum theory, hoping that it could be replaced by something in which statistics or probabilistic consequences could be eliminated from. But it was Niels Bohr who finally convinced Einstein through very famous debates that it is not your business to tell God what to do, and these are contained in the famous Bohr-Einstein debates, hotly debated at the Solvay conference in 1927, and quantum theory has come to stay. So this is now our picture, that the state of a system will be characterized by state vectors. These vectors will be labeled by whatever you can measure, and whenever you want to constitute a measurement, you will not be happy with constituting just one measurement and get one piece of information. You will like to get maximum information about the system. So like in the previous case, you get the momentum of the system and then you try to get the position as well, but you are stopped by nature that you can't get these two pieces of information simultaneously and accurately. Okay, if not this, can I get some other pairs simultaneously and accurately? If I can get one piece of information, there may be some other measurement which I can carry out which is not stopped by quantum theory, that quantum theory does not come in the way of getting additional information about the system. Maybe certain measurements are not compatible with each other, but some other measurements are. So you look for additional measurements and you try to look for maximum information that you can get, and then these set of measurements constitute what are called as complete set of compatible observables, because you can carry out the measurements, you measure one parameter, get a value, you carry out another measurement, get that value, record it, you come back and repeat the first measurement and you recover the same measurement that you had got on the first attempt, then it is a safe measurement, right? Then it is an indication of measurements being compatible. So these measurements are called as compatible observables, and the corresponding operators in quantum mechanics are called commuting operators, and one can do some simple algebra to show that if operators commute, the corresponding observables allow us to carry out compatible measurements. Now you can also write a wave function which is the coordinate representation of the state vector. So this is just the Dirac notation as it is called, and this is the Schrödinger-de Broglie notation as it is called, which is nothing but the coordinate representation of a state vector. And what one would like to get from this is not just one label A, whatever it is, but get as much information, get as many labels as possible which are compatible with each other. So you look for additional measurements which may come from measurement of some other property like B, and you get another eigenvalue equation, and this will then provide a second label for the state vector. So you try to maximize your information, and what we are going to make an attempt to do is to find out what is the maximum information we can get so that we can designate the state of an electron in the hydrogen atom. So that is the first question we are trying to answer in our story of the atom. So these compatible measurements are represented by commuting operators, and they constitute a complete set of commuting operators, and this is what we are going to search for so far as the hydrogen atom is concerned. So what are the good quantum numbers? What are the good measurements that you can carry out which will belong to this class of complete set of compatible observables? What is it that you can measure? So to begin with, let us recognize that as time evolves from yesterday to today to tomorrow, some properties which would not change, and these properties could be used to characterize the system, and what remains invariant under temporal evolution of an isolated system is its total energy. That, and the best example I could think of is this man who is everybody's hero in India. No matter what his age is, his abilities seem to remain invariant. Now this is to be taken in the context in which I mean it, because of course one can argue that his abilities seem to be growing with age, so I am not going to enter that debate here. But the essential point I want to make over here is that time and energy are canonically conjugate parameters in the classical sense, in the Hamiltonian sense, and under temporal evolution the energy of a system, of an isolated system, remains invariant, and you can actually measure it. And in quantum mechanics, this energy, which is the sum of the potential energy and the kinetic energy, this energy, which is the dynamical variable in classical mechanics, must be represented by an operator in quantum mechanics, which is the Hamiltonian. So you construct the Hamiltonian for the system, and you set up an eigenvalue equation for the Hamiltonian, and the eigenvalue can be used to label the system. So that is one index you get to represent the state of an electron in the hydrogen atom. You can label it by its energy, and then we ask, what else can you measure? You have measured energy, you have used that as a label to designate the state of an electron in the hydrogen atom, and we are asking, what else can you use to designate the state of a system of an electron in the hydrogen atom? And we immediately recognize that the hydrogen atom has got a rotational symmetry. There is just an electron and a proton, and the potential between them is the Coulomb potential, which is a radial potential. We recognize the spherical symmetry of this potential. So there is an intrinsic rotational symmetry, and we will spend a few minutes understanding what this rotational symmetry really means. Now if you have got some shape, and this shape is represented here with a box, with a square box with an arrow sticking out, so that it is somewhat asymmetric as well, and if you rotate this you get a new orientation, okay, and we want to ask, what is the operation you have carried out to get to the second form from the previous form? So there is a certain operation you have carried out, and this is the operator for which is the generator for rotations, and we are going to ask, what is the generator for rotations in quantum mechanics? So this generator for rotations, if it operates on a certain function, it will give you a new function, and the new function will have a similar profile, except that it will be turned through a certain angle. So that is the rotation operator, and it requires a little bit of simple algebra, and you can refer to Schiff's quantum mechanics to get the details. You can find rather easily, and this is going to work no matter what the shape is. It does not have to be a box with an arrow sticking out, it could be some arbitrary shape, and you could rotate it and arrive at a new shape through turning it, and the rotation operator is then, it has got the form that you find on this slide. that it is 1 minus I over h cross delta phi dot j, where j is the angular momentum. So, the angular momentum is really at the heart of this operator u. Okay. Everything else, you know, h cross and so on, it is, these are universal constant, this is just the Planck's constant divided by 2 pi. So, everything else is a constant. What is at the heart of the rotation operator is the angular momentum. So, the angular momentum is really the generator of rotations. Now, if you carry out these rotations, the interesting property of rotation is that these rotations do not commute, and you know what commutation is, that you come to college, you go back, that is commuting to your place of work and going back. So, that is commutation. So, you do anything and do the same thing in the reverse order, that is commutation. Now, what happens is that the rotations themselves really do not commute, and to illustrate this you can look at this simple picture. You have got a box which has got a black face in front of you and a red face on the side, as you can see in this picture, and what I am going to do is to rotate this about the 3 axes of a Cartesian coordinate system x, y, z, but I will perform these operations in different order. So, first I will perform a rotation through 90 degrees about the z axis, which will bring the red face to the front, and then you rotate it about the x axis again through 90 degrees, and you find that this particular object has fallen flat on its black face, and that is the picture you have for the final stage of these 2 orientations, 2 rotations carried out in the sequence in which I perform these operations. Now, what I will do is I will perform the same 2 operations, but in the reverse order. So, instead of carrying out the rotation about the z axis first, I will carry out the rotation about the x axis first. So, let us do that. The rotation through 90 degrees about the x axis keeps the black face in the front and the red face at the top, and now you carry out a rotation through 90 degrees about the z axis and the red face at the top rather than in the front. So, you see that the final orientations in these 2 is different, which essentially means that rotations do not commute, and this is intrinsic to the generator of rotations, which is the angular momentum. So, the angular momentum, which is the generator of rotations, really its components do not commute, and its Cartesian components x and y do not commute. These 2 operators, if you carry out these operations in the reverse order, the difference is actually IH cross JZ, and you have got a similar relation for the other 2 components. You have to contrast this with the linear momentum, whose components, Cartesian components, actually do commute. So, rotation is quite different from translations in homogeneous space. Now, this property in fact is used to define angular momentum. So, angular momentum in quantum mechanics is any vector operator which satisfies this algebra. Okay. So, you do not define it in terms of r cross p or anything like that as you do in classical mechanics. In classical mechanics we define angular momentum as r cross p, but one will not do so in quantum theory. In quantum theory, angular momentum is defined as some vector quantum operator whose Cartesian components do not commute, and their commutation relations are given by what we have on the screen. So, there are equivalent definitions, because if you just play with these commutation relations, you can immediately recover that the cross product of the 2 angular momentum vectors give you IH cross times angular momentum. This is again, there is no classical analog for this, because the cross product of 2 classical vectors would obviously vanish, whereas in quantum theory it does not necessarily happen. There are other definitions that the commutation of angular momentum operator with itself does not give you 0, which is a very strange result, but that is exactly what turns out to be the case. So, these properties are intrinsic to angular momentum, and these are in fact used as a definition of angular momentum. There is no other way of defining angular momentum in quantum mechanics. It must be defined in terms of the accommodation properties or some of the equivalent relations that you see on the screen. Now these attributes must be remembered, that it is a quantum operator, the angular momentum is a quantum operator, that it is a vector operator, and that it is an operator, so it must satisfy certain operator algebra and will be involved in the operator being a unit, being a quantity which will operate on an operand, namely the vector, and give you some algebra coming out of it. So all these three attributes have to be kept in mind while working with the angular momentum operator. Now let us understand these rotations, because all of these are fundamental to the designation of an electron state in the hydrogen atom, which is the simplest atom that we are going to work with. Now if you take any object and carry out some rotations, okay, or equivalently you can have an object and observe it from a coordinate system and rotate the coordinate system itself, okay. You can rotate the coordinate system, you can rotate it any which way, you can rotate it through a specific angle about a particular axis like this, or you can rotate it about an arbitrary axis, it does not matter what you do, okay. But you can rotate it, and then in this rotated coordinate system the components of a position vector, of every position vector, will obviously be different, and these components of the position vector will be related to each other by this relationship, that in the new frame they will be x prime y prime z prime, in the old frame they will be x y z, and you can get x prime y prime z prime by operating, by multiplying, by pre-multiplying this vector matrix, and you can just carry out a matrix multiplication to get the new column matrix which represents the position vector in the new coordinate system, in the rotated coordinate system. Now typically one can carry out different kinds of operations, or also you can include inversions or refractions in this, and typically these matrices will have a determinant which is either +1 or -1, and if you consider rotations alone, then the determinant of the matrix is +1, but if you include parity or reflection or inversion, then the determinant of the matrix will be -1. So these are the essential differences between a +1 determinant and a -1 determinant. So when we deal with rotations, and it is the rotational symmetry that we are working with, so parity or reflection is a different operation, you have left going to right, so x goes to -x, y goes to y, z goes to z, and this is represented by this operation over here, and this determinant of this matrix is obviously -1, as you can see quickly. Now this of course you see that the left goes to right, sometimes some students wonder why does not the top go to the bottom. Now no need really to panic, because depending on what kind of reflection you are talking about, the top will in fact go to the bottom, so no big deal about it. So anyhow, if you now gather together all the rotation operators, then they constitute a group, and this group is called as SO3, and O stands for orthogonal because the corresponding matrices are orthogonal matrices, their transpose and inverse are the same. It is called as a special orthogonal group, special because you are considering only those matrices whose determinants are +1 rather than -1 also, okay. So this is the special orthogonal group, and the number n, so this actually is a nomenclature which comes from group theory, and all of these are called as SON. This number over here, these are the number of generators, and typically the number of generators are given by this rule, n into n minus 1 by 2. So for n equal to 3, the number of generators are 3, and these are of course the 3 components of the angular momentum, okay. So the angular momentum are the generators of rotations in quantum mechanics, and there are these 3 generators. So the symmetry of the hydrogen atom is described by the SO3 group. Nevertheless, there is more to this issue, and we need to understand the hydrogen atom fully, and we are very soon going to discover that there is a little more flavor to this story than what we have met so far. So this is the rotation that we are talking about, and this is because of the central field symmetry of the Coulomb potential, which is a 1 over r potential. Now if you play with the angular momentum operators, which we have already defined, you can quickly discover for yourself that if you take the component of the angular momentum along any direction, it does not matter what direction it is, you take any direction in space and take the component of the angular momentum in that direction, which is given by j dot u, then these two operators also commute, which means that you can get simultaneous information about these two. And if you can get simultaneous information about these two, and if they also commute with the Hamiltonian, which they in fact do, then you can use the eigenvalues of the Hamiltonian, the eigenvalue of the operator j square, and the eigenvalue of ju, which is one of the components of the angular momentum operator, to designate the state of an electron in the hydrogen atom. So these eigenvalues really are labeled as n, l, and m, and this becomes the designation of a state of an electron in the hydrogen atom, and its coordinate representation gives you the de Broglie Schrodinger wave function. Now I will certainly not discuss the algebra of solving the Schrodinger equation, because that is something that you can find very easily in any book on quantum theory, but essentially the essential idea is this, that you have a time dependent Schrodinger equation and you can extract stationary states solutions of this, for which the time dependence is contained entirely in this e to the minus I e over h cross t term. So this has got the entire time dependence, and the time independent part psi r satisfies what we call as the time independent Schrodinger equation, and because of the spherical symmetry you can factor this into a radial part and an angular part. So you have, at least to begin with, a designation of an electron in the simplest of atom, namely the hydrogen atom. Now there is something strange which is happening here, and this is the question of degeneracy, and this is really a very interesting issue. If you look at the energy of the hydrogen atom, and you can do this by solving the Schrodinger equation, you will get the solution which pretty much agrees with the Rydberg-Balmer formula, and you get the 1 over n square formula with all the other constants. Now the interesting thing is that whereas the wave function must be labeled by n, l, and m, the energy depends on n alone. So why is it that the energy does not depend on L and does not depend on M? Now this is a question which is intimately connected with the degeneracy and the symmetry of the hydrogen atom. Now the question of degeneracy and symmetry of the system of the Hamiltonian, which give us information about the conserved quantities. These are the quantities which are conserved, and therefore they constitute the measurables, therefore they give you the good labels to designate the system. These are what you will call as good quantum labels for the atomic system, and you can certainly break the symmetry of the Hamiltonian and remove the degeneracy. That's always possible, but the hydrogen atom has got a very peculiar symmetry, that its energy is determined only by the principal quantum number for the bound states and not by the other two quantum numbers m and l. Now one must remember at this point that the entire hydrogen atom spectrum can be understood in these terms. This is the quantum mechanics of one electron atoms, but one must remember that the Rydberg series converges to a series limit beyond which there is a continuum, and these continuum states are also eigenstates of the very same Hamiltonian belonging to positive energy states above. So if you have your 0 of the energy scale over here, then these will be negative energy states and these will be positive energy states. So, we do not describe quantization in terms of discreteness of the spectrum, because discreteness of the spectrum is just a part of quantum mechanics. You also have continuum eigenstates in the positive energy part of the spectrum. So, discreteness is not the signature of quantum mechanics, it is a property of bound states in quantum mechanics. Now, the question we are trying to address here is why the energy of the bound states depends only on the principal quantum number. Now, you can understand it from the spherical symmetry as to why the energy does not depend on m, because m, if you solve the Schrodinger equation, it comes from eigenvalues of the operator Ju or Jz, which is one of the components of the angular momentum, right. So, the angular momentum, so Jz acting on this vector give you an eigenvalue equation, and this becomes your label for the hydrogenic quantum state, but this u could be any direction in space. It could be pointing toward like this or toward this, it could be pointing toward east or west or hell or heaven or wherever, okay. So, it really does not matter which direction it is in which you choose the vector u, and this comes from the rotational symmetry of the potential. So, because of the rotational symmetry, there is an invariance with respect to m, and one can understand that the energy will not depend on m. So, the degeneracy with respect to m can be understood in terms of rotational symmetry. So, there is, you know, that for every L quantum number, m can take 2L plus 1 values, m going from minus L to plus L, and there is a 2L plus 1 fold degeneracy, and this can be understood in terms of the rotational symmetry. What we do not understand is why there is an n square fold degeneracy. The degeneracy is not just 2L plus 1 fold. 2L plus 1 fold degeneracy comes from the different 2L plus 1 m values that you can get as eigenvalues of the operator Jz, but L itself for bound states can take different values from 0 through n minus 1, and if you sum over these 2L plus 1 values from L going from 0 to n minus 1, you get n square. So, there is an n square fold degeneracy. As a matter of fact, to be precise, there is a factor of 2 missing over here. This will come from the 2 states that an electron spin can take, but I will come to that part of the story a little later. So, for the time being, we will ignore spin and ignore the fact that there is a degeneracy which is twice n square, but we will talk about the n square fold degeneracy, and we cannot really understand the n square fold degeneracy from rotational symmetry alone, because the rotational symmetry only tells us that the energy is independent of m, the azimuthal quantum number, but it does not tell us that it is also independent of L, which is the orbital angular momentum quantum number, and all the 3 quantum numbers n, L and m are required to designate the quantum state of an electron in the hydrogen atom. Now, you get some kind of clue, because if you look at another hydrogenic system, which is the sodium atom. Now, the sodium atom has got some resemblance with the hydrogen atom, because the sodium atom has got 11 electrons, and you can look at the 11th electron, which is the outermost electron in the 3s subshell, as if it were in the field of 11 protons in the nucleus, shielded by the remaining 10 electrons, giving you an effective charge of plus 1 at the center. Now, this is the classical picture. It does not quite work that way, but at least it gives us a start, and it tells us that there is some similarity between the hydrogen atom and the sodium atom, but then there also are differences, and the differences are manifest right over here, because all of you would have done experiments with the sodium vapor lamp in your physics lab, and you would have seen the sodium D1 D2 lines, and these D1 D2 lines come from transitions from an electron in the sodium atom in the 3p state to that in the 3s state, and this transition is possible at all because the energy of 3p is different from 3s, which means that in the sodium atom the energy depends not just on the principal quantum number but also on L. Now, this is a suggestion. In the hydrogen atom, the energy depends only on the n quantum number, only on the principal quantum number, but in the sodium atom it depends not just on the principal quantum number but also on the orbital angular momentum quantum number. So what is the difference? And this really these are the famous D1 D2 lines that we get out of the sodium vapor lamp, and if we understand this question we will understand the n square fold degeneracy of the hydrogen atom. So a hydrogen atom has got this n fold degeneracy, and the answer to this comes from this issue, this difference between the sodium atom and the hydrogen atom. So let us consider what this answer is. This is sometimes called as the accidental symmetry, or it is sometimes also called as the dynamical symmetry. This was explained by Vladimir Fock, and in my mind this is one of the major contributions to understanding of atomic physics. The Fock symmetry of the hydrogen atom is a very major step, and this model was developed by Vladimir Fock in 1935, and it explains the n square fold degeneracy of the hydrogen atom. Now here is a factor 2 which I am writing in anticipation of a further degeneracy which comes from the two states that an electron spin can have, but I will come to that a little later. So we can understand this to a certain extent also from the semi classical or the old quantum theory, okay, the old quantum theory which is the Bohr-Sommerfeld quantum theory, but we can also understand it in terms of the modern quantum theory which does not depend on these orbits. But let us see what the old quantum theory suggests. So you have got the planetary model in which you have got electron orbits in these ellipses. Now what is interesting is that this ellipse remains fixed, it does not precess, and the rotational symmetry or the conservation of angular momentum does not require you to assume that the ellipse must be fixed, okay. That equal areas are swept in equal time, which comes from Kepler's law, comes from conservation of angular momentum, but that is not sufficient to explain that the ellipse does not precess, because if it were to complete one orbit and then go on to another orbit and precess like this, and if you saw this precision from a distance it would look like the petals of a rose more or less, and this is sometimes called as a rosette motion. So that there is no such rosette motion for the Bohr-Sommerfeld orbits is not explained by rotational symmetry alone. So there is an additional symmetry, and this, if you do not know what that symmetry is, it is certainly not the rotational symmetry, because rotational symmetry we have already discussed, we have found that it accounts for the degeneracy with respect to the m quantum number, but there is this additional degeneracy, additional symmetry, which we can at best call as an accidental symmetry, and in fact it turns out to be called as a dynamical symmetry, and this is the symmetry of what is called as the Laplace-Runge-Lenz vector, and this vector is defined as P cross L minus mk E rho, and it turns out, and one can do this by doing some simple algebra, it will take you about 5 minutes to do it on a scratch piece of paper, that this vector defined as such will be a constant, its time derivative will be 0. So if you take dA by dt it will go to 0, but only if a certain condition is satisfied, not otherwise, and the condition is that the potential must be a 1 over r potential, okay. If it is not a 1 over r potential, then this vector will not be constant, and this vector, if it is a constant, then it is a constant both in magnitude and direction. Its direction is along the semi major axis, and this direction is not going to change, the vector being constant, and therefore the ellipse does not precess. So that is the symmetry which is the dynamical symmetry as it is called, because the corresponding force must be a 1 over r square force, the potential must be a 1 over r potential, and the corresponding force, which is where dynamics comes in, which is why it is called as the dynamical symmetry, and this is called as the Laplace-Runge-Lenz vector. Lenz interpreted the hydrogen atom quantum mechanics in terms of this vector, the Runge-Lenz vector, so it is also called as the Laplace-Runge-Lenz vector. Now, we will not want to use old quantum theory, not the orbits. So, Pauli came up with the corresponding quantum operator for the Laplace-Runge-Lenz vector, okay, and this must be understood to understand the quantum mechanics of the hydrogen atom. So, the quantum Laplace-Runge-Lenz vector is constructed from the classical Laplace-Runge-Lenz vector, which we first write in units in which k is equal to 1 and m is equal to 1. So, this is just a matter of choice of units, and in terms of these units, p is the linear momentum, L is the orbital angular momentum vector operator. What Pauli did was to symmetrize this vector product. So, he constructed this operator as half of p cross L minus L cross p, and these are not classical cross products, otherwise the cross product of A cross B is equal to minus of B cross A, and they would just kill each other. That certainly does not happen, okay. These are quantum operators and there are commutation relations that one must respect. So, in quantum mechanics, Pauli constructed this operator and he got the properties of the hydrogen atom, and this belongs to the whole algebra of the Fock symmetry which I mentioned earlier. There is a very nice article in the American Journal of Physics written by Burkhardt and Leventhal. They have also come up with a book which was published a few years ago called Topics in Atomic Physics, and this is a nice source which I will recommend to read about this particular topic of the quantum Laplace-Runge-Lenz vector, or which is the Pauli-Lenz vector as it is called. And as a result of this, there is an additional quantity which is conserved, and the symmetry of the hydrogen atom is not just SO3, but it is actually SO4. So, with the index n equal to 4, the number of generators will be n into n minus 1 by 2, which is actually 6, and these 6 generators are the 3 components of the angular momentum as we recognized earlier, but now we have 3 additional generators which are the 3 components of the Pauli-Lenz quantum vector. So, this gives us the algebra of the hydrogen atom, and in the case of the sodium atom we understand why the 3p and 3s do not have the same energy. It is because the Laplace-Runge-Lenz vector is not conserved for the sodium atom. It is conserved for the hydrogen atom, because what happens in the sodium atom is that if you take the outermost electron and take it to the asymptotic limit, take it to r tending to infinity, take it very far away, and if it is really sufficiently far away from the rest of the atom, then it is going to see the 11 protons screened by the remaining 10 electrons, and it sees an effective charge of just 1 unit, and it sees the 1 over r potential just as an electron in the hydrogen atom. However, if the electron gets closer to the nucleus, then it is going to see all the remaining electrons, okay, and as it goes, as r tends to 0 close to the nucleus, it will actually see a potential which goes as minus z over r, and you can see some of these details in the book Physics of Atoms and Molecules by Branson and Joshain in chapter 8, and you will find that the potential becomes more attractive in the case of sodium atom than what it is in the hydrogen atom. So, the potential is not a strict 1 over r over the entire range, it is a confluence of these two figures, okay, and you cannot represent it analytically using any simple straightforward equation or simple analytical function, but you can easily recognize that it is not 1 over r in the entire space, which was, if you remember, the necessary condition that the Laplace-Runge-Lenz vector must be a constant. So, it is not a constant, and there is a precessional energy, and that is contained in what is called as a quantum defect. There is a very nice formalism named after Mike Seaton. It is called as a quantum defect theory, and this quantum defect must be taken into account for any many electron atomic system. This is a topic of great interest in modern atomic physics as well. So, the earliest review, some of the earliest reviews you can find in the article by McIntosh which came in American Journal of Physics, which are nice articles to read, and then the group theory of the SO3, the SO4 you can find in this article. And then even in recent years, this is a paper from just a few years ago in 2006 by Melbianen and Jan Michael Rost on the multiple expansion, the Fock symmetry of the hydrogen atom, which I just mentioned. So these are topics of current interest for those of you who would read ahead of your classes. Now there is a further twist. Not only is the energy of 3p different from 3s, there are two levels belonging to the 3p. There is actually a doublet, and these doublets are the reasons that you get the two d1 and d2 lines, which are separated by what we call as the spin orbit splitting. So there is this whole idea of spin, and the spin is very intimately associated with Pauli's name, who lived between 1900 and 1958, and it was in 1924, in the very early days of quantum mechanics, that Pauli proposed a two-valued quantum number for electrons. He proposed a quantum number which should have two values. It could be A and B, it could be alpha and beta, it could be 0 and 1, it could be up and down, it does not matter what you call it. All that Pauli was aware of was that it must have two values, and only by coming up with this could he really account for the filling up of shells in the periodic table, because there is a closing of the shell in the periodic table, so that when you go to the last group, which is the group of the rare gas atoms, the helium, neon, argon and so on, right. So there is a certain filling, after which you must go to the next row in the periodic table, and to account for this Pauli had to invent a two-valued quantum number. Now he did invent a two-valued quantum number. He went on to propose that no two electrons in an atom can have the same four quantum numbers, which is what we call as the Pauli's exclusion principle, but though no reference to spin is made yet. Okay, all that Pauli talked about is a quantum number which must have two values, no reference to spin. Now the idea of a half integer spin, as we are aware of, this came much later, and this had to wait for two experimentalists, Uhlenbeck and Goudsmit, and they had to come up with this idea of spin, and let us see how this idea comes about. So Sommerfeld turned this idea to Heisenberg, because there were other experiments which were being carried out, experiments carried out by Zeeman, spectroscopy experiments. Heisenberg introduced the idea of half integer quantum numbers, but this shocked Sommerfeld very much. Sommerfeld said that okay, now you have half quantum numbers, then you will have 1/4 and then 1/8, then 1/16, and you will be back to a continuum. So one thing that we knew from quantum mechanics is that these must be integers. So what was the great idea in introducing half integer quantum numbers? So in fact this idea was rejected in the early days of quantum mechanics, and Bohr was also unhappy, and in fact Pauli himself mocked at this idea and ridiculed and rejected this idea. Now it was for Uhlenbeck and Goudsmit, and these were brilliant students of Ehrenfest, and Goudsmit was off to Germany on a private visit with his father, and he was advised to go to the laboratory of Paschen and carry out some measurements over there, and it was during this work, experimental work in Paschen's laboratory, that Uhlenbeck and Goudsmit came across some spectrum, and what they found is that there was a certain forbidden line in the spectrum that they had seen, and they made an attempt to understand this forbidden line. So there was a line which could not be explained by the quantum mechanics as was known at that time. So they tried to understand this, and in fact Goudsmit goes on to tell us that when he reported this matter to theoreticians, they said that maybe it was a poor experiment, forget it, ignore it, and nobody paid much attention to this. But Gaudsmit and Uhlenbeck did. They thought that there was more to it than just a bad experiment, that there was some physics in it, and what they did was to invent this idea of spin. It came out of nothing. There was no real model, and in fact Uhlenbeck called it as abracadabra, like some sort of jadoo, that it just came out of a hat. Gaudsmit also felt that it was some sort of a numerology, and it just seemed to work, and if it works, might as well accept it. So this is what led to the idea of the electron spin. And when we think of an electron spin, these are the pictures which come to our mind, but an electron spin has absolutely nothing to do with any of this. There is absolutely no classical analog. So if you see any of these pictures to explain the idea of an electron spin, it must be dismissed. There is absolutely no classical analog. The electron spin is essentially an angular momentum, and what is an angular momentum? We have defined it. It is such a vector operator in quantum mechanics that its components jx comma jy will give you IH cross jz, or j cross j equal to IH cross j. It can be understood only in terms of these commutation relations, and the electron spin is an angular momentum, and if you take the eigenvalue of the operator j square, you will get the eigenvalue which is in units of h cross square, which will be half into half plus 1. So the half actually comes from the eigenvalue of the angular momentum operator for the electron. So that is where it comes from. And as I mentioned, Pauli had himself rejected this idea. This is a picture of a letter which is available on the internet. This is a letter which Thomas wrote to Gaudsmit, and he pointed out that Kronig had believed in the spinning electron, and he reported this to Pauli, who was the first person to whom he reported, and Pauli ridiculed the whole thing so much that Pauli was also the last person to whom Kronig had the courage to discuss this. So Pauli just mocked at that idea and dismissed it, and this was Pauli's early stand on electron spin. Pauli had a very strange, very curious life, very sad one in some sense. He was deeply attached to his mother. His mother had committed suicide. His personal life was quite in a mess. His marriage had lasted just a few weeks. He used to drink. He had to be thrown out of a bar because of excessive drinking, and Ehrenfest, when he met Pauli was quite an obnoxious person, and Ehrenfest in fact told him on his face that I think I like your papers better than you, and no surprise Pauli replied that I think I like you better than your papers, but the two eventually went on to become fairly good friends. So anyhow, Pauli subsequently introduced the 2x2 matrices, and these are the famous Pauli matrices, and these are intimately associated with Pauli's name now, and also with electron spin, which links Pauli with spin in a very complete fashion. And Pauli predicted the Nutri law in 1930, and in 1940 he proved the spin statistics theorem of the quantum field theory, that particles with half integer spins are fermions, particles with integer spins are bosons, and it was the actual origin of the electron spin in fact comes only from Dirac's relativistic quantum mechanics. So it has got an origin only in relativistic quantum mechanics. It has no place in Schrödinger form of quantum mechanics except by some ad hoc mechanism. You can always plug it in from the outside, but it really does not belong to non-relativistic mechanics at all. It comes from relativistic quantum mechanics, which was formulated by Dirac in 1928, and this prediction of the electron spin, which gives an angular momentum, and this is the silver atom which is neutral, and this is the famous Stern-Gilbert experiment, and there is an unpaired electron on the outside, and its angular momentum provides it with a certain magnetic moment, and you can separate the spin up and the spin down components. So these were actually seen in the Stern-Gilbert experiment. So this is a tribute to Stern-Gilbert in a memorial which is in honor of Stern and Gilbert. This was inaugurated in recently, less than a decade ago in 2002 at Frankfurt. Now one should remember that this experiment was done with silver atoms, and the atoms, each atom is electrically neutral. But if you were to do this experiment with an electron, if you send a beam of electrons through the Stirner-Gilrack experiment, you are not going to get separation of this. The reason is that the electron has got not just the spin, but it also has a charge. So there is a Lorentz force, Q times V cross B would come into play, as a result of which if you plug in the uncertainty principle into this, it turns out, and one needs a little bit of algebra to show this, that you cannot really separate an electron beam into two components in a Stirner-Gilrack experiment. Now this Stern himself was quite opposed to the idea of quantum theory, and in fact in one of his earlier analysis of the Bohr model, he ridiculed the idea of Bohr so much that he said that if this nonsense of Bohr were to be proven to be correct, we would actually quit physics, because he had no interest in a physics in which Bohr's quantum theory would have any place at all. Statistics does enter quantum theory in a big way, not just from the uncertainty principle, but also from the fact that elementary particles are indistinguishable. Now as a result of this, these two kinds of particles, which are half integral particles or half integral spin particles or integer spin particles, these are either the fermions or the bosons, and it can be stated very easily, and I quote from Feynman from volume 3, that it appears to be one of the few places in physics where there is a rule which can be stated very simply, but for which no one has found a simple and easy explanation. Very easily you can say that, okay, if the particle has got half integer spin, it must observe Fermi-Dirac statistics. If it is integer spin, it should observe the Bose-Einstein statistics, but there is a lot more to this, and I think this is a fairly involved issue. I will recommend Tomonaga's book, The Theory of Spin, and one can find some further pointers on this subject, but I will not discuss this idea any further, and I will go on to discuss the physics of atoms with more than one electron. So the hydrogen atom we understood to some extent, we understood the symmetry of the hydrogen atom, first the SO3 symmetry, then the SO4 symmetry, the poly length symmetry, the sodium atom spectrum, the degeneracy of the hydrogen atom. But now what are we going to do if we are to work with an atom with many electrons, because after all the periodic table has got more than 100 atoms, and except for the hydrogen atom everything has got more than one electron. So more than one is many, so we will call it as a many electron system. And if you now formulate the Schrödinger equation for a many electron Hamiltonian, for a many electron atom, then the Hamiltonian will contain not only the kinetic energy operator for each electron and the potential energy in the field of the nucleus, but also the electron repulsion. And how do you estimate that? Now if electrons were these particles separated by this distance, then q1 q2 divided by this distance would be the term which would go here. But you can't really do that, because the electrons are not these classical charged particles at these specific points in Bohr-Sommerfeld orbits. These must be described by their own wave functions, which are probability amplitudes. They have their probability amplitude modulus square, which will give you the probability density, and the probability density multiplied by the charge will give you the charge densities. And at any point in space you will have a certain charge density of each electron which repels a corresponding charge density at some other place, and these charge densities multiplied by the tiny volume elements around them will give you the charges in those volume elements, and then you can talk about the Coulomb repulsion between these charges. In other words, to get this 1 over r1j 1 over r12 term which ought to go into the Hamiltonian, you really need the wave function, and this is the problem, because you had hoped to get the wave functions by setting up the Hamiltonian and from its solutions get the wave functions. And now you are saying that, okay, give me the wave functions first, and only after you give me the wave functions I will construct the Hamiltonian. So you have a problem, and this problem was solved numerically if only in an approximate way, and the way to do it is to construct some sort of an approximate wave function in terms of which you can construct the Hamiltonian, go ahead and solve the Schrodinger equation, get a solution, and ask if this solution is the same as the assumption you had made earlier. If it was, well and good, otherwise go ahead and change it, and you can change it as many times as you need to till you get what is called as self consistency. So this method was developed by D.R. Hartree at this British physicist, and he developed this method of self consistent field, but I already mentioned that the electrons are Fermi particles, so they must observe Fermi Dirac statistics, so the wave function must be antisymmetric, and when you solve this problem using Hartree's self consistent field method, respecting the antisymmetry of the wave functions as well, then you refer to the technique known as the Hartree-Fock method, and this method is known as Hartree-Fock method of getting self consistent field solutions. Hartree in fact designed this differential analyzer in 1935, which came out of these small toys like Mechanos, and he actually built this differential analyzer to get numerical solutions. And the heart of the Hartree-Fock theory is contained in this relationship which is known as the Koopman's theorem, that if you get the energy of the n electron system and you remove one electron, but you pretend that all the remaining electrons retain their original forms, that those do not flex. So this approximation is known as the frozen orbital approximation, and in this frozen orbital approximation, if you now get the energy of the n minus 1 electron system, which will be the removal of the after removing one electron, so you produce a hole in the kth state, so the occupation number of the kth state goes to 0, then the energy difference of this turns out to be what is an eigenvalue like creature in the Hartree-Fock equation. So this is known as the Koopman's theorem, who was also a student of Kramer's. Koopman's went on to do economics, and he got the prestigious prize which is instituted in the memory of Alfred Nobel, so it is the economics equivalent of the Nobel Prize, and Koopman's went on to get this prize. So this is known as the Koopman's theorem, and this contains the heart of the Hartree-Fock theory. What it assumes that the electron wave functions do not change on the removal of one electron. So this is the frozen orbital approximation, and Hartree in fact contributed a lot to the development of electronic computers. So in fact when the first electronic computer, this numerical integrator and computer which was developed in the US, Hartree was in fact asked to go and contribute to its development, and in this model the many electron wave function is written in a determinantal form which is named after John Slater. So this is called as a Slater determinant, and in this the arguments of the function, the single particle functions, are the spin orbit coordinates of the electron, and the subscripts are the sets of 4 quantum numbers. So these represent the electron states in a n electron atomic system. Now Hartree in fact understood the powers of the computers, and when he was appointed to the chair in Cambridge, he in fact said that it may well be that high speed digital computers will have as great an influence on civilization as the advent of nuclear power, and today we certainly know that this has indeed come out to be true. Now what I want to mention are the electron correlations. Now the fact that the wave function of a many electron system must be antisymmetric, that 2 electrons they have these these half integer spins, okay, as a result of which their dynamics is correlated. Okay, there is a certain correlation, which is why the many electron wave function must be antisymmetric for all Fermi-Dirac particles, and this is the result of a correlation. But this correlation is coming from statistics, it is coming from the Fermi-Dirac statistics, so it is called as a Fermi correlation, or it is called as a statistical correlation. It is also called as spin correlations, but because it is coming from the essential property of the electron spin. However, there are other correlations, namely the Coulomb correlations, because the approximation made in the Hartree-Fock formalism that the many electron wave functions do not flex, they do not change when you produce a hole, cannot really be true, that there will be these density fluctuations, as a result of which the many electron correlations must be taken into account, and these are known as Coulomb correlations. And what this needs is a many body theory. This needs field theoretical methods. These methods are, you know, at some level known as second quantization methods. You can develop diagrammatic perturbation theory, write these approximations in terms of Feynman-Goldstone diagrams, and these are some ways of solving the problem of Coulomb correlations in a many electron system, whether it is an atom, a molecule, or any extended bulk object of condensed matter. And these are some of the people. The field is very vast, the number of people who have contributed to this field is enormous, and I will make no attempt to be comprehensive, or this is not the full story in any way, but these are some of the major contributors to this field: Jan Lindeberg, Walter Johnson, Alex Delgado, Mike Seaton, he passed away rather recently, Fano passed away somewhat recently, and lot of atomic physics in today's domain of frontier physics deals with the question of correlations. I already mentioned what these correlations are. There are these two kinds of correlations, there are the spin correlations and the Coulomb correlations. In addition to that, there are the relativistic effects. So the relativistic models of dealing with correlations really need to be developed, and these are some of the frontier problems in the field of atomic physics. They impact all domain of physics, including simple things like the photoelectric effect. Now all of you would have done this experiment in your undergraduate laboratory. This is the Einstein's photoelectric effect, and this is the interpretation of the Hertz experiment, Hertz and Leonard experiment in the 19th century, which Einstein explained in 1905, which was cited in Einstein's Nobel Prize award. And there is a lot more to photoionization than just measuring the intensity of the photoelectron current, because you want to see, as any physicist will like to do, that in addition to one property, what else can you measure. And as we discussed in the earlier part of this lecture, that whatever you can measure is limited by the uncertainty principle. There are certain measurements which are compatible with each other, some measurements which are not. So you look for complete set of compatible measurements. So you look for transition probabilities of the ionization of an electron into the continuum when it absorbs a photon, and you measure these transition probabilities or the intensities of the corresponding transition. These are measured and recorded in what are known as cross sections for the process. But in addition to this, what are the other compatible measurements? And if you carry out a measurement of all of these, you carry out what is called as a complete experiment. So for a complete experiment on photoelectric effect, it is possible to measure the photoelectric ionization cross section. You can measure spin polarization parameters, you can measure the angular distribution asymmetry parameters, what are the different directions in which the electrons come out, okay, what is it that this direction is with reference to? It is with reference to the incident direction of the photon and the direction of polarization of the electric vector. So you have a frame of reference, and with respect to these directions you can ask what is the electron yield in, and when you measure all of this you get complete information about the picture. and in studying this you need to employ very sophisticated theories. You need relativistic models, you must take into account the electron spin, you must start with the Dirac equation, not the Schrodinger equation, you must take into account all the electron correlations, and you really need a very sophisticated relativistic many body theory. I would like to mention here a very important contribution which is not very well known by S. Chandrasekhar, the very famous astrophysicist, and what he contributed was to the understanding of this matrix element, that when you have a transition from an initial state to a final state which is affected by a certain coupling, then this is the transition matrix element. And what Chandrasekhar pointed out, that in the context of photoionization, for example, this matrix element can be evaluated in various alternative methods, and these are the length form and the velocity forms of the matrix element, etc. So I will not go into the details, but this is an important contribution of Chandrasekhar which I will like to mention here. I will, as we approach the concluding part of this talk, I would like to mention some of the very exciting things which are happening in the field of atomic physics in current research domains. One is the determination of the fine structure constant, and this is a very important factor. In fact, Feynman says in his book on in the strange theory of light and matter, this QED book, that it has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number on their wall and worry about it, because what it is, why does it have the value that it does have, does it change, at what rate does it change, is it just a free parameter, or is it there is more to it? If it changes, it probably changes at a rate which is given by this 2.9 into 10 to the minus 15 per year. So though these are some of the limits which have been found, and there has been a study by John Webb. This study is from astrophysics spectroscopy of stellar spectra. What John Webb's group did was to study light from metallic atoms and gas clouds coming from stars which are very far off, which are like 15 billion light years away, not 15, sorry, 12, the age of the universe itself is about 13.7 or thereabout. So this light is coming from deep space, about 12 billion light years, that was the estimated distance, and what he found is that there is a little bit of, you know, from the shift of the spectra compared to the spectra as are observed on Earth. It seems that these atoms in distant deep space probably were somewhat different, and it might be a suggestion that the fine structure constant may be really changing, even if very slowly over passage of time, and this has got important consequences on the standard model of physics. This is, to a certain extent, it has got a place in the standard model of physics, but there may also be some suggestion that there is physics beyond the standard model. And in fact, the measurement of alpha is one of the most challenging experiments in physics that people are carrying out. These are some of the estimates of 1 over alpha, and look at the accuracy with which people are measuring alpha. Means this is an experiment which was conducted at Harvard in 2004. This was a part of a PhD program of Brian Odom, and here the uncertainty of the Harvard G value, this is a measure of alpha in a certain sense, I will not go into those details, and this uncertainty is in fact less than the width of the point itself. So it is very accurate, high precision measurement. So this is a challenge to the young students amongst you, that these are the kind of experiments which people are really working with. Then in astronomy in particular, means you have not just the fine structure because of the spin orbit splitting, but there is also the hyperfine structure, because the electron nucleus has got a spin which couples to the electron spin, and that will generate alternative states of singlets and triplets, and you can have transitions between them. This is the famous 21 centimeter line that you can see from anywhere in the universe, and a lot of probes in astrophysics are searching, carrying out astrospectroscopy using this particular transition. There is this Lamb shift which goes beyond the Dirac solution for the hydrogen atom, for the relativistic hydrogen atom, because Dirac's quantum mechanics will tell you that all states with different L whose quantum numbers n and j are the same, these must be degenerate. So 2s half and 2p half will have the same energy according to the Dirac model. Nevertheless, if you look at the hydrogen atom closely, the 2p half has got a somewhat different energy, and this is due to the famous Lamb shift, and this again requires many body field theoretical analysis. I will not get into that. You can do lots of things with atoms these days, and this was the beginning of the nanoscience or the nanotechnology. Feynman in fact asked this question: what would happen if you could actually pick an atom one by one and manipulate its position, keep it at different places, and actually engineer various mechanical models out of it. And the first instance of this achievement was this picture that you see, which is xenon atom on nickel's surface, and this was done by Eichler and Schweizer, reported in Nature in 1990. And what they did was to take 35 atoms of xenon and position them using a scanning tunneling microscope, kept the first one over here, the second one over here, the third one over here, and they went on to build these letters IBM. So this was an amazing achievement, that you could actually manipulate atoms one by one and build, you can actually build gadgets using this. The atomic spectroscopy, the hyperfine structure, it provides you means for frequency standards, so atomic clocks can be built using this. You do not have to go to the Jantar Mantar anymore, but you need very high precision measurements of time. Time is a fundamental parameter with reference to which anything else is measured. So atomic clocks are being built. You can cool atoms, you can slow them down by subjecting them to, you can just the way you can take a billiard ball and stop it by quenching its motion in different directions, by arresting it this motion, and you can apply these pressures using lasers, and this is the general field of laser cooling. And using this you can really slow down these atoms, and you can slow them down. The slower an atom is, the colder it will be, right, because temperature after all in a certain sense is a measure of its kinetic energy. So you can slow down these atoms, and then you have this entire domain of cold collisions and ultra cold collisions. You go down right up to 10, this field of 10 to the minus 6 to 10 to the minus 9 Kelvin. So these are extremely low temperatures. You do not want these temperatures even in Chennai, but in the labs, yes, I think it is a great achievement. And what happens when you slow down an atom? Its momentum goes down, and the momentum, when it goes down, the wavelength increases, right. So the slower the atom, the larger would be its wavelength, and the wavelength can be made to increase, and it can become larger and larger. Why does it have to be just as much as the Bohr radius? It can go well beyond it. It can go beyond the radius of an atom, beyond several atoms, maybe tens of atoms, and if you do so, then you really get condensation. So this is the overall field of Bose-Einstein condensation, and very sophisticated techniques are used to achieve this state of matter, which is a very special state of matter which is found only in the laboratories. The atomic clocks have become very precise. Let's look at the clock uncertainty. This is a picture from the NIST website, and if you look at the clock uncertainty measured in units of nanoseconds per day, then you really have extremely accurate clocks, and these are used in GPS navigation and so on. So the Bose-Einstein condensation of course was predicted by Satyendranath Bose and Einstein way back in 1922, but it was realized only in 1995 by Cornell and Feynman, and they could really cool down atoms to very low temperatures, extremely low temperatures. Now, before we conclude, there are a few other things I would like to mention. So, we are just in the next few minutes. We have also already understood the importance of symmetries in physics, because these symmetries give us the quantum numbers. Okay, we found that the Pauli lens symmetry explains the quantum mechanics of the hydrogen atom. It explains why the 3p and 3s have different energies in sodium atom, but not for the hydrogen atom, right. That is because of the Pauli lens symmetry, the SO4, and the symmetries that we talked about earlier, like rotations or translations, these are continuous symmetries. The Laplace Runge-Lenz vector is a dynamical symmetry, but then there are other symmetries also, like the discrete symmetries. Okay, and the discrete symmetries that I would like to draw your attention to are the P, C and T, the parity, charge conjugation and time reversal, and together these three are conserved according to the standard model of physics. So, this is the Lorentz symmetry, and the parity violation was predicted by Yang and Lee and observed by Madame Wu, that processes in mirror reflections really need not conserve parity, and this was found in weak decay, in the electroweak interactions, in the beta decay experiments studied by Madame Lu, and it is not really quite obvious, and I would like to quote here from a very nice article in Reports on Progress in Physics by Boucher and Boucher, that the concepts of parity conservation and parity violation cannot really be considered to be just intuitive. There is a lot of deep physics which is involved in this, and this goes into the CPT symmetry, and what is important in the standard model of physics is the integration or the unification of the weak interaction and the electromagnetic interaction in the Glashow-Weinberg-Salam model. What this did was to unify the weak interaction and the electromagnetic interaction, and one can obviously ask that if parity is violated in weak interaction, would it not be violated in electromagnetic interactions as well, because the two interactions are essentially the same because of this unification. So, indeed there are very interesting experiments which are being carried out on parity violation in atomic physics, and I will like to mention these are fairly involved subjects which I will not get into, but mention them as exciting areas of research for those of you who will carry out further studies. And then there is the CP violation which was known, but CP violation would also predict a time reversal asymmetry. Now, the time reversal operator is an anti-unitary operator, and under this operator the angular momentum actually changes its sign. So, if you now ask if an elementary particle has got a dipole moment, okay, now this is a strange question in some sense, but you can ask this question: does it have a dipole moment, and if it has, under what conditions would it be seen, and under what conditions it will not be seen. So, you can, if it has a dipole moment at all, the direction will have to be defined with reference to some direction. So, you suggest that you choose the direction of the spin as the direction along which you indicate the dipole moment, but then under time reversal the angular momentum changes its sign, but the charge distribution, the dipole moment should not change its sign. So, what value can it have so that it will not change when the sign is reversed, and the only number that comes to your mind is 0, because plus 0 and minus 0 are the same. So, going by this argument, one would think that an elementary particle should not have any dipole moment. Now this is quite acceptable with common experience, but then the fact of the matter is that CP violation was discovered in 1964, and if CP is violated, then T also will have to be violated, because it is CPT together which is conserved according to the standard model. So there is scope to search for violation of time reversal symmetry, and this can be carried out by looking for electron dipole moment, and these are some very fascinating experiments which are being carried out in the field of atomic physics, and not just atomic physics but also in molecular physics, because it turns out that if there is any dipole moment at all, then it would be enhanced in certain heavy polar molecules, and YBEF is chosen as a candidate, and these experiments are of course cheaper than what you could carry out at the Large Hadron Collider. So this may, some of the explanations will be within the scope of the standard model of physics, or there may be some physics beyond the standard model, I do not know, but these are some questions which atomic physics is addressing at the very frontier of fundamental physics. I would like to mention here a different application of the time reversal symmetry in atomic physics, more from the point of view of conventional atomic physics. And if you look at this particular experiment, that you want to probe anything, and one way of probing any target is to shoot some particle. A prototype for this could be an electron, and you can think of this target as an ion, and I am discussing here an electron ion collision, and from this you study the properties of the target. Now this electron could hit an ionic target, and there may be a complex formed which decays into another ion and an electron, but you can get this final state also by having a photon absorbed by an atom, because what this photon could do is to knock out an electron and leave an ion as a residual species. So you can get these two processes, and one would expect that there is some kind of relationship between these two processes, because they have the same final state, but the initial states and in fact even the initial ingredients are quite different from each other. And these are the experiments that if you have a scattering experiment, then you have the entrance channel which is unique, but if you do this experiment in a time reversed or in a motion reversed state, then the motion reversed picture of this would be what you would get in photoionization. So actually the photoionization and the electron ion collision, these two processes are also related to each other by time reversal symmetry. So these are important considerations in atomic physics, and there are in all this relativistic effects, correlation effects are the major things to be studied, many body perturbation theory, field theoretical methods, entanglement is another area of important research in atomic physics, CPT violation which I just mentioned, questions about whether or not there is physics beyond the standard model, the scanning tunneling microscope and the atomic force microscopes give you the tools to manipulate individual atoms to make engines and so on, and the study of atoms is important because atomic physics is in some sense the laboratory in which you can study relativistic and many body effects, and what you learn from this you can carry this with you into the physics of molecules and clusters and condensed matter, which you have to understand for developing these modern gadgets and so on. So to understand this, the atomic physics really give us a working laboratory, and the single atom, I will conclude this talk by just telling you that a single atom is mostly empty. So there is a huge amount of space inside it, empty space, and if you manipulate this space, if you use this space well enough, you can actually store a lot of information. And one example over here is that of this picture that you see, that this is a hydrogen atom in an excited state, an electron in a hydrogen atom in an excited state with principal quantum number equal to 50. Okay. So there are 2500 angular momentum states, and if you construct appropriate superpositions of those, okay, you can produce places of densities and cavities, and by manipulating these computationally the word optics has been written on this atom in an excited state. So there is a lot of information that you can actually store in it. So this is a nice picture. So with this I will conclude this talk by quoting Feynman, and I would like you to read this with me. And he says that if in some cataclysm, which I had to refer to a dictionary to find the meaning of this, any violent catastrophe involving sudden or extensive changes. So if something like this were to happen to the world and all the information is lost, and then if you were to leave some information for posterity, for future generations, to build science from the beginning again, all over again, if all the information is lost, what is the one little piece of information that you would like to leave? And this is Feynman's analysis of that, that if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. So this is the most important piece of information that could be passed on. So the atomic physics really is at the heart of this. It occupies a central position in the entire domain of science and technology. It is the single most important piece of information that Feynman would have us left for posterity if all other scientific knowledge were to be destroyed. So thank you all very much for your patient listening. I'll be happy to take some questions. Any questions from the audience in front of me, or any questions from, there is some audience in remote stations. I see IIT Patna, IIT Ropar, IIT Guwahati, IIT Kharagpur, IG Kar. Oh, is that Alika there?
Yes.
Hello Alika.
Yeah, hello, how are you?
Good.
Yeah, this was really very, very interesting, your presentation, and I can imagine in fact, the amount of effort which you have put in collating all the things taken right from high school physics to the next century almost, I will say.
Thank you.
So this is really an enormous effort. Now I have two very small questions. One thing is that when when we talk about the cooling of the atoms and all those things, and so the de Broglie wavelength, it will become very large. In fact, when you were explaining it, we just worked out the de Broglie wavelength. If we cool down to 10 power minus 9 Kelvin, it comes out to be, assuming the atom, and so it comes out to be 0.005 centimeter. What is the physical meaning of such a long wavelength? Because if we just compare that from the size of the atom, it is 10 power 4 times more. So does it mean that if we have a linear array of these atoms, okay, and they are cooled, all of them are at 10 power minus 9, so does it mean that the effect of one atom sitting at one corner will be felt up to the 10 power 4, the atom sitting at the 10 power 4th position, or what? I want to understand this.
Well, actually the atom in a certain sense loses its individual identity. I mean, it's a different state of matter altogether. It's a different state of matter because it would overlap on neighboring atoms, and what you really have is a condensate. Yes, you really have a condensate. You really have a condensate. Now those temperatures are very hard to achieve. Those slow motions are very hard to achieve, but what people working in the area of Bose-Einstein condensation are trying to do is to slow down these atoms as much as they can, so that they can get a large body of a completely different state of matter, which we cannot really classify in terms of matter as we understand it in the conventional sense, means in the conventional sense we talk about glasses, we talk about liquids, we talk about solids, we talked about gases, and we talk of matter made up of as if it is made up of various atoms, but here the very idea of an atom has to be modified because what you have is a whole system. This is the condensate. So you really do not talk about individual atoms, but you have the properties of a different state of matter altogether. So it's very hard to get, but yes, that's what people are working with, and they are trying to get this. This has got. Yes.
It's difficult to imagine also that what is going to be the matter and what is going to be its property.
Well, it will have completely novel properties. It will have completely novel properties means there are some speculations, people are hoping that it will have certain properties, and if you exploit the quantum properties coming out of the principle of superposition and entanglement, you could even use it to build quantum computers. So the quantum computers, one channel, one path to get to the quantum computer could be via the Bose-Einstein condensation, because it will have amazing properties involving entanglement and superposition.
Another question. Can I entertain another question?
Yes, please.
Can you entertain another?
Yes, yes,
okay.
please.
The second question is that this when we talk about the D lines, that is actually this question is much more basic. So when we talk about the D lines for the lithium, we have 2p to 2s transition, sodium 3p to 3s transition. But why we do not the reason that why we do not see for the hydrogen, maybe the splitting is so small that we cannot see it.
No,
because the charge is.
No, not at all. For the hydrogen atom, there is total degeneracy with respect to the L quantum number. The hydrogen atom eigenvalues are completely independent of the L quantum number. So 2p 2s, 3p 3s, 3s 3p 3d, 4s 4p 4d 4f, okay. No matter what the L quantum number is, for a given principal quantum number you have only one energy for the hydrogen atom. So there is no question of having a transition between 3p and 3s. It is not a matter of the energy difference being small. There is no energy difference, there is total degeneracy. It is because the potential of the hydrogen atom is a pure Coulomb potential, it is a strict 1/r potential. Whereas in any other atom, whether it is lithium or sodium or anything else, the potential is 1/r only in the asymptotic limit, only as r tends to infinity, but as r tends to 0 the potential is different. So it is not 1/r throughout the whole space, and that is what ruins the conservation of the Laplace-Runge-Lenz vector symmetry. So that is the Pauli-Lenz symmetry that I talked about.
Yeah, thank you.
Well, I want to thank everybody who has come here. I want to thank NPTEL, its faculty, its staff, Mr. Kannan here, and the audience over here, and the audience in remote stations, IG Car, IIT Patna, ICIT Ropar, ICIT Guwahati, IIT Kharagpur, and I do not know if there is anybody I am missing, but IIT Gandhinagar is also connected, I am told. So whoever has been patient enough to be a part of today's event, I am very grateful to all of you. Thank you all very much. Goodbye for now.